Okay, good morning, people. The other class we ended up with the section on compaction. We did some we looked at a few problems as well. So today we intend to introduce a rather a new but an interesting topic, which is on effective stress. So in this topic, I'll try to cover up the section on effective and total stress. We look at the difference between the two, and if given a time, we'll also do a small problem. We'll also introduce soil capillarity. So we'll introduce what's phreatic surface, that's the groundwater table, and also look at what is soil capillary in soils. So that's called as capillarity. So let's begin. I'd like you to look small sketch, the cartoon which has been drawn on the right hand side. The sketch shows that's the ground level. So usually ground level is shown by a hatch. You know, a hatch is drawn below the straight line. It shows that's the ground surface. And if an inverted triangle is drawn, it shows the groundwater table. So we'll look at this groundwater table in a while. But what it represents is that the surface of the water is this level. If you look at a point, an element at the depth z, as shown over here, okay. So and if I say the unit weight of the soil is gamma saturated because we assume that the soils below the water table is all the voids are filled with water. So we take gamma saturated. And if I follow this analogy, that what is the overburden, the total overburden at this level. So total overburden, we call this as total vertical stress. So total vertical stress at depth z. Take an example that as if the legend Atlas, legend Atlas. I think it's Greek legend. He's carrying the earth on on his head at this level. So that's the overburden you're carrying. So it effectively would mean gamma saturated. That's the unit weight of this soil times z. That's the total vertical stress. Total vertical stress at this level. What about the pore water pressure? Pore water pressure, sometimes people call us just pore pressure, assuming with an assumption that this always will be water unless it's contaminated soil. So you're dealing with normal soil, it's assumed that it's always water. So we call this as pore pressure or pore water pressure, PWP. Now this pore pressure is given by, again, if I follow the same analogy, as the unit weight of water times the depth z. So that's gamma W times z over here. And the difference between the two, that means total stress minus pore water pressure. This by definition is our effective stress. Sometimes we like to call this as intergranular stress, but only called as effective stress, labeled as sigma prime. You may like to call this as sigma dash. I'm more comfortable with sigma prime. That's a sigma equals to sigma minus u. That's total stress minus the pore water pressure. You look at this in detail today. So the pore water pressure, we call this as neutral stress. Neutral stress, why? It's quite easy to understand this, that if I throw a bucket of water on the floor and ask you to walk, you can't possibly walk. Because thin film of water on the surface of the ground, you possibly can't walk because water is unable to carry any shear load. Okay, so that is why we call this as neutral stress. It's neutral. It's also called as neutral because the three stress components, vertical, horizontal, and the third component which comes out and hits you, the three stress components are of same magnitude. You're familiar with calling it as a hydrostatic stress. So in soil mechanics, we always like to say water has no shear component. It cannot carry any shear load. That is why we call it neutral stress. Move on. It's sigma, that is total stress, and sigma prime effective stress. They have both normal and shear component. Both on a plane you can have shear stress, which is the sliding stress, and the normal stress. These two have both the components. However, it is only the total stress and the pore water pressure which can be measured. The total stress can be measured as we looked at the cartoon just a slide before, that you have a point somewhere in the ground and you want to look at the overburden. You look at the total stress, that's sigma for us. Pore water pressure can similarly be calculated looking at the depth below surface in case you have a steady, no groundwater flow condition. However, there are instruments to measure total stress and effective stress. However, I apologize, there are instruments to measure total stress and the pore water pressure. However, there are no instruments, you cannot possibly measure effective stress. Effective stress is only deduced, it's manifested as a result of observation of total stress and pore water pressure. Let's look at the next slide just to exemplify this thing. You look at this, the figure on the left. In fact, this is a triaxial setup here at IIT Bombay. Our master student do this consolidated undrained test. We look at this later, but I would like you to focus on this small circle over there. This small circle shows a small transducer which will measure the pore pressure. This pore pressure transducer, can be fitted, and it's like a diaphragm, a small diaphragm on which the water hits, and the deflection of the diaphragm tells you how much of pressure is induced on the diaphragm. Similarly, if I have another instrument which also works on a diaphragm, but it's slightly different, I can measure the total stress. Now over here the figure is not very clear, but I have zoomed in one of the circles somewhere over here. That small instrument over there will measure the total stress. Okay, so the bottom line of this slide is you can measure the total stress, you can measure the pore water pressure, but you cannot measure the effective stress. So when we speak about effective stress, how important is this? Because it's something which you cannot measure, but we still say it's important. In fact, it's the most significant factor or most significant concept on which the entire strength of the soil, or let me generalize this statement, the entire mechanical behavior of soil depends on. You may in one of the earlier lectures we said the three most important features of soil we are interested is the strength, the compressibility, and the permeability. Depending upon which field you are, one of these properties or one of these results would be pretty important for you. So all these, the strength, compressibility, and permeability, they depend on effective stress, which is sigma prime. In other words, if effective stress, which is sigma prime, increases, your entire mechanical behavior can drastically change from rather a poor soil to a better soil. So that's how significant the sigma prime is. Compare this to the change in total stress, which is sigma, and the pore water pressure. If take an example of if these two values increase, but the effective stress remains the same. If you look at the equation which we had just a few slides back, in which total stress was equal to effective stress plus the pore water pressure. So if on the left hand side of the equation, if you're just slightly keen, I can go back to that particular slide. That's over here. I have total stress equals to effective stress plus the pore water pressure. That's the equation I speak about. So if I have a combination of total stress and the pore water pressure, if I increase this and parallelly increase this, in other words, the change in effective stress or the delta sigma prime, that's the change, is zero. There is no change. In that case, let me go back to our current slide. There is no change. Your mechanical behavior of the soil will not change. All the three, compressibility, strength, and permeability, may not change. So let's look at effective stress rather in detail. Over here I have a small cartoon on the right hand side. Please look at this sketch over here. It it's just a a very simplistic model which represents two soil grain. I would say it's an idealistic model because soil grains will never have a very smooth surface. This more or less looks like a spherical surface. So in these two models, if I look at this carefully, if I say capital A, apologize if the figure is not very clear, but that's capital A, which is total area. So I'm looking at two-dimensional figure, but take an example that it's third dimensional comes out and hits you. So it's the area, it's the complete area, capital A, and if I say this AC is the area of the contact of the two particles, AC is the area of the contact. So in other words, capital A minus AC would be the area over which I have this empty space. Okay. So this empty space, if I fill with water and I induce pressure, pore water pressure over here, pore water pressure, we have represented pore water pressure by small u in these slides. So that's small u is the pore water pressure in the area capital A minus AC. So if I look at the equilibrium of forces, okay, equilibrium of forces would mean if I apply a force P, capital P over there, the part of the force which is transmitted through this grain to grain contact should be this, capital P should be this component, this small p, capital P prime over here, this is capital P prime, plus the force which is transmitted through the water, the vertical normal force which is transmitted through water. So just to put it in English, this capital P is, we are looking at equilibrium of force, is the left hand side, should be equal to the force which is transmitted through the particles, which is P prime, plus the force which is transmitted through the water. So if U is the pore water pressure or the pore pressure, so this times the area. So the area is total area minus the AC, area of the contact AC. Okay. So the first equation is pretty much straightforward. If I divide both left and right side by capital A, I get something like this, which is P by capital A equals to P prime by capital A plus A minus C by capital A times U. Look at this carefully. P by capital A is the total load divided by total area. It's our sigma, total stress, which we have defined sigma. P prime by A is, if I, or conveniently, if I just represent this as sigma prime for the time being. Remember sigma prime, I'm just trying to represent this P prime by, P prime is the force which is transmitted through the contact, interparticle contact, and A, capital A is the total area. Okay, I've just represented by sigma prime. I'll explain this sigma prime in a while. Let's look at the next component. I have A minus AC by capital A. So that results in 1 minus AC by capital A. If I look at this AC, AC is the small component which is the contact between the two particles, and A is a large component. In fact, this whole thing I can say it tends to 0 because AC tends to 0, it's too small. So in other words, this would be 1 minus 0 or 1 times U. Okay, so I have this equation which is sigma total stress equals to, I have represented this by sigma prime plus U for water pressure. This sigma prime is our effective stress. Okay, we have called this as effective stress, but mind you, we have divided the force, which is the interparticle force, by total area, not the small area. So I'm dividing by total area. So can I say this effective stress is a fictitious quantity? It's not the true interparticle stress which is transmitted, because my denominator is capital A. So we sometimes, many of us argue, effective stress is in fact is a fictitious quantity. Okay. Let me go on to the next slide, please. We have conveniently assumed that the plane, the interparticle plane, is horizontal. Okay, let me go back, please. This plane we say is horizontal, right? So all the force are transmitted through interparticle contact, it's horizontal. There could be millions of other particles as shown in the cartoon over here. You know, all the particles are randomly placed. And when we speak about such particles, we speak about granular soils. So the previous slide, in fact, when we spoke about the particle to particle contact, we were effectively dealing with granular soils. Okay, so in granular soils, the particles are randomly placed. So the interparticle contact, if I want to join a line between particle to particle contact, the line would be wavy. Okay, it's going to be wavy. It's no longer a straight line. So are we really correct in assuming that, you know, the stresses which are vertical stresses which are transmitted through the particle are transmitted along a horizontal plane? In many engineers say or claim that, you know, it's quite convenient to assume this to be horizontal plane because for the sake of simplicity, yes, it makes my life very simple if I just assume this plane to be simple. But if you look at really at a macro level, a large level, meaning you look at the same cartoon from very far off, you're looking at a macro level, this wavy plane, if I assume to be straight line, it's really not so incorrect. So for most practical purpose, I would say it's not incorrect to say that, you know, my plane or the plane through which the vertical stress is transmitted from one particle to the other particle is a straight line across all the particles. Now up to the previous slide we said, you know, I emphasized that, you know, the concept from of one transmitting the stress to the other particle, this concept is valid for granular material. However, a few of our previous slides back, we said, you know, the particle to particle, at least for for fine grained deposits, the particle to particle are not actually in contact. Those fine grained particles have a film of water. If you recall, we spoke about clay crystals, clay mineralogy, and the clay crystals have a film of water. This film of water would not directly allow the particle to the stress which is transmitted from one particle to the other to go through. Okay, so this in fact defies all the logic we have, you know, stated in the previous few slides. However, Skempton, with a lot of work, Skempton in late 50s and early 60s did a lot of experiments on clay soil, that's our fine grained soil, and observation that the principle of effective stress, meaning total stress equals to the pore water pressure plus the effective stress, is valid even for fine grained soil. So this concept was validated through experiments, and rather than, you know, an analogy of using one particle in contact with the other. You should note that this principle of effective stress is not valid for partially saturated soil. In fact, there's this partially saturated soil is another major branch of soil mechanics, and usually we don't teach this at the undergraduate level. Even for master's level, we try to introduce some degree of introduction to partially saturated soil, but this branch of engineering is mainly for research. So for our simplistic case, we will say that this concept is only valid for saturated, fine-grained and coarse-grained soils, not for unsaturated soil or saturated rocks or concrete. Let's introduce a term called phreatic. It's quite you know, it's quite a, you know, fancy name given to groundwater table. So we call it as phreatic. So that's the phreatic surface. Sometimes we also like to call it as gravitational water, and the other term is capillary water. Both the water can easily be removed from you know, by just heating the soil you know, normally at up to 100 degrees if there is no organic. Speak of water, let me have some sip please. So I'm going to discuss a bit on phreatic, that's the groundwater. That's the first one. Phreatic or the gravitational water, its few assumptions or few well-known features. It will completely saturate the voids. So all the voids which are below the phreatic water would be saturated. So this figure or the photograph on the right shows this person probably dug a pit, dug a pit somewhere here and saw some water seepage, and with time, in fact, the water seeped and filled up to a constant level. So that's the filling which this guy sees. Okay, in fact, he's quite standing on a very risky platform. So this water, steady water, which now seeps and then reaches a steady value, which you can clearly extract. It won't go up because this is a steady level. Below this water table or the phreatic level, the voids are assumed to be fully saturated, and this is not an incorrect assumption. It's a good assumption. This water can be removed from soils by drainage. So in case there was, I have a pit, I can remove this water and then gradually, depending on how quickly the water seeps out and backfills the pit again, it will help me to drain the water either continuously or at regular interval. So the upper surface of this water table is called as phreatic surface. So that's the phreatic surface or the groundwater table we are looking from the top. And the pore water pressure at this level balances. So the atmosphere pressure above the water table balances the water pressure at the phreatic level. So can I safely say the pressure at the phreatic level would be same as the atmospheric pressure? I'm going to speak about this in the next slide as well. Okay. At the phreatic surface, so we say pore water pressure. Usually when you read textbooks, you say pore water pressure at the phreatic surface is 0. So at this level, we say pore water pressure is 0. Now there is a rider to it. Do we mean the gauge, the GAUGE, the gauge pressure, or the absolute pressure? So gauge, as the name sounds, you're gauging with respect to something. We did say at this level the atmosphere pressure is balanced. So if I gauge this with respect to atmosphere, meaning whatever reading I have, I balance it out or consider the datum as my atmospheric pressure. So if this is my groundwater table level, and if I say this is at atmosphere pressure, and any other pressure change with respect to atmosphere, I gauge it. So this is my datum level. That in that case, my gauge pressure at this level will be 0. Okay. In opposed to this, I have a second term which is absolute pressure. So absolute pressure at this level would be 1 atmosphere. That balances the atmosphere. I hope you are aware 1 atmosphere is approximately 100 kilopascal. Okay, just an approximate number. Okay. So in usual practice, we in fact ignore this gauge. We just write pore water pressure at the groundwater table level is 0. In fact, we mean the gauge pressure is 0. But in many textbooks, we just ignore the term called gauge. If you have any questions, we'll take up questions towards the end, last 10 minutes or so. Okay, we have good time today, in fact, to do a problem as well. So let's quickly go through the other water, which we spoke about, the capillary water. The capillary, elementary physics has taught us what is capillary. And we're going to use that analogy, what we studied in school physics. Okay. So capillary, what does capillary mean? That the groundwater table, we say anything below the groundwater table is soil is saturated. But even a small region above the groundwater table level remains saturated because of the soil capillary, because the water tries to hang up onto the various soil particle, and because of this hanging up, it climbs up. Consider that it tries to take a ladder up to a certain height. This ladder up to the certain height depends on a few features, and we will look at those features. Okay. Those features, if you recall surface tension in physics, surface tension was the tendency of a fluid to reduce its exposed surface. So it tries to reduce the exposed surface to the smallest possible, because of which it tries to hold on to the various particle and tries to climb up. This climbing up balances to some extent. So it is the water tries to adhere to the soil part, to the adjacent particles, and also because of the the inherent the bonding. This cohesion is rather strange to be used here, but bonding between the water, which the molecules, which does not try to water to break up, it also tries to hold it. Let's look at the next figure, which is makes it easy for us to understand what was said. If you recall your elementary physics, when we had a capillary tube, and if you dip the tube in water, the water in the tube rises to up to some level. In fact, you can take an ordinary straw, the straw which your Pepsi or Coca-Cola straw, and you dip that straw, you will still find that the fluid rises up to some extent, although it's more prominent in capillary tube because the diameter of the tube is smaller. In fact, when we speak about diameter, let's take an analogy that the diameter of the tube is similar to your pore or voids, the voids between the soil. So if I say the voids between the soil represent, if the diameter of the tube is equivalent to the voids in the soil, I am aware, because of this capillary tube, the phenomena, the adhesion force which causes water to rise. This is our elementary physics. It balances the molecular bonding between this water, which helps to reduce the surface area. Okay. In case of water, because of reduction in surface area, I think it's concave, bending down, it's concave. So if I want to balance this, the weight of water, if I look at the equations which balance this, so I have the same cartoon over here. Now in this case we have the forces which are shown. So the weight of water in this column is represented by W. P atmosphere is the atmospheric pressure which acts from the top. T is the surface tension. So surface tension, it normally acts at an angle. Let's say this angle is alpha, and T, the units of T, I hope you're aware, is force per unit length. That's the surface tension. So if I say the force which is acting downward is the weight of this column. The weight of this column is the force which acts downward. Force which act upward is the vertical component of the surface tension. Okay, the vertical component of the surface tension. So if I want to write this in equation, I have this hc times pi d square by 4. Okay, hc is the height of this column. It's usually measured from bottom. The small change in height because of this weight of this water in the small height is kind of ignored. So hc is measured. So hc times pi d square by 4. That's the volume of water in this column times the unit weight of water. So that's the force which acts downward. So equals to the upward force. So it's T remember was the surface tension. It had units of force per unit length. So if I multiply this T, cos alpha is the vertical component, T cos alpha times the perimeter pi d. That gives the upward component. If I equate the two, okay, and knowing that, let me just move to next slide. I have equated the two. Please ignore this for the time being. Look at the right hand side. Okay, if I have equated the two, knowing that for pore water alpha is 0. Okay, clean glass tube and pore water alpha is 0. We are going to use this assumption for soil. Okay, it's rather a question how much this would be valid, but assume this to be valid. And capital T has a for water and at fixed temperature, it's 20 degrees or 22 degrees. I believe it's 20 degrees, it's 73 millinewton per meter. So it's fixed quantity. If I plug this in 73 over there and take alpha to be 0, I get Hc, which is the capillary height, equals to 4T, equals to 4. I have plugged in 73 over there. So I get Hc equals to 0.03 by small d. this HC comes out to be in meters if I put small d in millimeters. So this equation has taken care of dimensions. So this is plugged in millimeters, but the answer is in meters because the unit, this constant over there, takes care of it. So if I use this analogy of capillary tube in my soil, I can say this HC is my capillary height, the height of over which the water will rise above the water table, okay, within the small grains, and d, small d is the particle size. Okay, we are going to look at this equation very carefully. Okay, this is still I would say a very generalized form of equation. Okay, we'll just look at it in detail in the next few slides. Look at the cartoon over here, the sketch over here. This horizontal line is a water line. That's the water table, groundwater table. And I'm still looking at the tube. The capillary tube is still with me. So I've inserted the tube over there. Remember, below the water table, the first slide of today showed that below the water table, the pore water pressure increases linearly. Remember, we said it was unit weight of water Z. So that was a linear increase with Z. Pore water pressure increases, and this is positive. So the analogy we follow is, if the pore water pressure increases, this value is positive. And when we look at shear strength, we will look at this positive nature much in detail. But for today's class, I would like you to appreciate that pore water pressure is positive below the water table. Okay, below the phreatic surface. Above the phreatic surface, we say that the water exists under capillary tension. Okay, so it's tension. So the same line, if I extend this upward, in fact this line, because the gradient is the same, okay, I have now HC, which is the height measured above the water table, times unit weight of water. That's the tension thing. Okay, so it reaches up to height HC. So the pore water pressure in this capillary zone, D, let me call this as pore water pressure in the capillary zone, obviously would be the distance measured from here to there, which is HC times gamma W. And because this one is the compressive one, I must say below water table is positive, above water table is negative. So I have a minus sign over there. Okay, so HC, I remember HC was as minus 4T small d times gamma W. So I have gamma W, which is eroded off. So pore water pressure is this particular expression. Now I would not like you to remember all this, because only expression over here, if I go back, is this over here, HC equals to 0.03 by small d. However, this approximate assumption you still use in real soils, and there are some approximate equations, or I would say semi-empirical equations, which are very similar to this particular expression, which we use for our soils. Okay, this particular analogy explains the sketch over here. Now I would like you to look at only on the left hand side of this wall. Please ignore the cartoon, the sketch which is drawn on the right hand side. We are only going to look at the left hand side. This particular bottom line shows the water table. So our assumptions from the first few slides are this: all the voids below the water table are filled with water, saturated. From here to height HC, we have just calculated on the very first in the last few slides. This is a capillary height of water. Okay, in other words, theoretically, my water should be saturated from here to there, but this is not the case. So, because your voids are not so uniform as a capillary tube, your soil particles are not so uniform throughout. So what happens is, there could be a small break in capillary. So you have good particles over here, nice out, a soil capillary rises up to some level, but then you have chunks wherein the soil capillary is broken at this level, and somewhere over there the soil capillary goes still higher. In other words, you have a partially saturated soil somewhere here. So if I extend this analogy throughout, I will have partially saturated zone for the top few distance within this height HC, because the soil capillarity gets broken. Okay, so you can go home and go through this slide, which shows that the water will only fill up wherein the voids are, there's a continuity in the voids, okay, or it will fill up only the narrowest voids. So I have a new height which is HCS. This HCS, for the time being, I'm not so worried about why we have used this particular nomenclature, but it represents the height over which the soil will remain saturated. Okay, and definitely it's less than the capillary height. This height HCS, okay, let's give, people have made a lot of observations, and this height HCS is in fact for various soils has been listed in this table. Now again, without even looking at memorizing the numbers, remember these are just data coming in from some field, and they're not, the numbers are not really important for us, but what is important is to look at the range. Okay, for coarse sand it's hardly few centimeters. Okay, that's 0.03, 0.15 meters, it's hardly few meter. Medium sand, it can go up to a meter or so, that's the worst case scenario, it can go up to a meter. For fine sand, it can extend up to few meters. For silts, it's up to tenths of meter, but for clay, definitely it's larger. It's quite, it can, for clay, it can go much higher. There are some examples, fine examples available in literature, wherein because of the soil capillarity in clay, the earthen dam, the upstream side of the earthen dam, because the water there starts to rise up because of capillary, the water in the dam has gone down. So I think you can refer to some textbooks which have pretty nice examples. So the last slide is some empirical relationships which have been developed, very similar to the one which we have used from the capillary tube analogy. Tezargi and Peck in their textbooks have HC, which is the capillary height, again in centimeter, have a same empirical equation. Okay, there is a constant C which has a range of 0.1 to 0.5, and D10 is the particle size, refers to from grain size distribution. You read out what is the uh, particle size corresponding to 10% finer than. So E is the void ratio. There's another equation which is again going around some textbooks, which HC is given as 0.03. This is D. This is our standard equation, but rather than D, we replace by 20% of D10. Okay, that's the other form of equation. So usually, it's not a bad idea to at least remember what HC equals to 0.03 divided by D, provided this D I fit in millimeters. Okay, so we're going to pause over here. We still have about 10-15 minutes to do a simple problem, and thereafter we'll take some questions. Okay, please, if you have questions, please hold on. I'm going to upload a document. I'm sorry, I'm not sure if this document has been allowed? Okay, sorry, apologize. I'm now right clicking on it, and you can download this file, okay, this particular lecture notes. Meanwhile, while you download, I'll also upload another document. Double click. And this is today's, we'll do a small column on this. Probably it should not take more than 10 minutes, 10 maybe 15 minutes. Okay, let me allow download to this. Now I would not like you to jot down or copy this, because you can always, this is download, you can always download this and read it at leisure at home. Let me quickly go through this question. This question says, there's a ground profile. Please look at this cartoon over here, this profile. So that's the ground surface, and at 3 meter depth you have the groundwater table level. So the degree of saturation in this zone is S is the degree of saturation is 0.4 or 40%. Specific gravity of the sand from surface to 5 meters is 2.65, and also the void ratio is constant of 0.6. Okay, from 5 meter to 8 meter depth you have clay. Again, specific gravity and the water content is given. Remember, below water table, both these soils should be saturated. The question is, there are three parts to this question. The first part is, draw the total neutral and effective stress. So total stress, neutral stress, effective stress up to 8 meter depth. It says neglect capillary flow. So whatever we did in the last 10-15 minutes, it says ignore the soil capillarity. The second thing is, then part B says what happens if the groundwater table reaches the surface, what is the effective stress at 8 meter depth, and C says the same groundwater table level now is 1 meter above the surface, and what is the effective stress at 8 meter depth. So let's look at first part. Okay, quickly go and start from first part. Sorry, there's a blue thing. Download किया ना? Yeah. Please, please download the document. We'll start with this question. Now, to begin with, we are given the unit weight, sorry, we are given the specific gravity void ratio. If you recall, for the total stress, we do need the unit weight. We say unit weight times the depth gives us the total stress. We do need the unit weight. The unit weight is not given in this question. So if I look at this carefully, I have given other various parameters to help me to deduce the unit weight. Let's look at that. The topmost one is sand, and above the water table the sand is not fully saturated. So I remember gamma bulk. Okay, let me write this as gamma bulk. If I recall, this is given as GS plus SC divided by 1 plus E whole times gamma W. Right? This is something we have done before. And gamma bulk for sand, if I say gamma B, now just B and brackets I'm just writing sand. This is the sand above the water table. This should be again GS plus SC divided by 1 plus E. So GS for sand is given as 2.65, correct? So 2.65 plus SE, S is given as 0.4 and void ratio is given as 0.6. This whole thing divided by 1 plus 0.6, and I multiply this by 9.81. Okay, apologize if it has gone outside the screen. Okay, so that is my gamma bulk. So gamma bulk sand, I can write this as, if I plug in the numbers, I should have an answer which says 17.72 kilonewton per meter cube. Okay. Now if I follow the same analogy, I should get gamma saturated for sand below the water table. The only thing is, now the degree of saturation should be 1, S is 1. So gamma saturated I write as SAT, and again sand I get 2.65 GS plus SE, S is 1 plus 0.6 divided by 1 plus 0.6 whole thing times 19.81. This should give you an answer which is 19.93 kilonewton per meter cube. Okay. Now we have the unit weight of sand both above and below. What about unit weight of clay? So gamma saturated, again clay. Okay, this is clay. Now if you look at the numbers, I have been given GS for clay and water content for clay. Okay, if I use the same expression, I have gamma saturated for clay equals to GS plus E divided by 1 plus E, gamma W. E is not given, okay, but I'm aware, if you recall your first lecture, I had SC equals to WGS, okay, remember this equation is important as well as this equation is important. So in this case, S is 1, I'm below water table, clay is below water table, so E equals to WGS. So I can replace void ratio by W times the specific gravity. So I have gamma saturated for clay equals to GS for clay is given as 2.7 plus I have WGS. WGS is 0.45, 45% is the water content times 2.70 divided by 1 plus again WGS 0.45 into 2.7, whole thing times 9.81. If I plug in my number, I should get gamma saturated for clay equals to 17.34 kilonewton per meter cube. Okay, I'm going to use these numbers. So this is for clay, this is for saturated sand, and that's for bulk sand. I would need to use these three, okay, in this problem. So I'm going to save this paper so that I keep refer to this paper for my part A. Part A says deduce the total neutral and effective stress. So at up to the entire depth. I'm aware at surface total stress recall it's sigma equals to 0. There is nothing at the surface. Pore water pressure is also 0. So in other words, effective stress equals to sigma prime equals to sigma minus u, which is also 0. Okay. Let's look at an important thing at 3 meters, 3 meter depth. At 3 meter depth, I use this analogy, total stress. Okay. Total stress equals to the unit weight of sand, the bulk unit of sand. If you've written down this figure somewhere, it was 17.72. So I have 17.72 times the depth, which is 3 meters. This should give you an answer 53.16 kilonewton per meter square. That's total stress. Remember, this is sigma for us. What about the pore water pressure? Okay, now at 3 meter depth we are at the phreatic surface, and at the phreatic surface we say the pore water pressure is 0. Okay, it balances the atmosphere, so the gauge pressure is 0, and we use the gauge pressure, for our engineering practice, and do remember the word gauge is normally omitted, it's not spoken. So this should be 0. Okay, so effective stress sigma prime equals to 53.16 minus 0 equals to 53.16 kilonewton per meter square. Okay. Now let's look at the next one, which says at 5 meter. 5 meter is the boundary of the sand and clay. So at 5 meter depth. Okay. I have the same analogy. Total stress. Okay, let me change the color of the image. It looks much better. Total stress sigma equals to, again at 5 meter I have 3 meters of the partially saturated sand. So that's 17.72 into 3 plus 2 meters of saturated sand. So 19.5 93 times 2, that's 2 meters of saturated sand. It should give you a number which is 93.02 kilonewton per meter square. What about pore water pressure? Okay, pore water pressure is U. Okay, if you look at the the figure, I'll bring out the figure again. Okay, we are somewhere here. We are looking at 5 meter depth. That's this level. Your pore water pressure is 2 meters. You're looking at 2 meters below the groundwater table level. Okay, so pore water pressure should be again the unit weight of water 9.81 times 2. That gives you a number which is 19.62 kilonewton per meter square. So therefore effective stress equals to sigma prime equals to sigma minus u, which is 93.02 minus this value 19.62. If I plug this in, I should get a number which is 73.4 kilonewton per meter square. Okay. Now I would like you to try the third one, at leisure, which is at 8 meter depth. Okay. If you do that, the 8 meter depth, okay, you would have stress, you would have the effect, you would have the total stress, you would have, okay, let me show it over here since it's pushed away. You would have the total stress, effective stress and the pore water pressure at 3 meter, 5 meter and 8 meters. If you do that, the question says draw the stress distribution diagram. Okay, the stress distribution diagram should look something like here at the bottom. So that's the total stress distribution. Like I said, you've got to try this at home. The last one, we've just done 53, 93, that's the total stress. Pore water pressure starts from the water table, which is from there, and it goes down to up to 49. You got to derive this value. We have done 19.62, and the difference between the two gives the plot of effective stress distribution, right? So let me right click this and say, okay, you please go home and download this thing and see that how it works. Okay, let's look at part B of this question. This one is there? Okay, thank you. So part B of the question says, if the water table, this water table goes up to the ground level, what is the change in effective stress at, what is the new value of effective stress at 8 meter? And we have 3 minutes. So, oopsies. So total stress at 8 meter depth. Okay, sigma equals to the partially saturated sand or gamma bulk of sand. So gamma, I'm sorry. Now the water table is at the surface. So the entire sand becomes saturated up to the surface. So I have gamma saturated of sand. Okay, that's the figure over here. This entire sand is now saturated. So I have now saturated unit weight of sand times the 5 meters. So gamma sat times 5 plus gamma sat of clay times 3. Okay, so the sand is now saturated, so I have that gives me 19.90 times 5 plus gamma saturated of clay. If you look at the numbers, it was 17.34 times 3. Should give you a number which is 151.67 kilonewton per meter square or kilopascal. What about the pore water pressure? Now the water table is at the surface, so pore water pressure is for the throughout 8 meter. So 9.81 times 8 gives me a value of 78.48 kilonewton per meter square. And the difference, which is effective stress, equals to total stress minus the pore water pressure, which gives a value of 73.19 kilonewton per meter square. Okay. Please compare this value to the value which you will derive at home, and please make out a statement. Statement should be that the effective stress has decreased when the water table has gone up. Okay, so the rise in water table ensures that the effective stress decreases. Now the third part, I would like you to try it at home again, which shows what happens if the groundwater table is 1 meter above the surface. Okay, in that case, you would still get the same answer. It's a wonderful thing to see that the answer would not change if the water table is at the surface or 1 meter above the surface. Okay, okay, therein you can make a statement that any fluctuation of water above the ground surface, okay, any fluctuation of water above the ground surface does not change the effective stress. Let me just put it in English. In groundwater table, above the surface would not result in change in effective stress. Okay. Okay. We come to the end of this. Okay, we have approximately 2 minutes. I'm not sure if we can take a good question. Okay, we can take a question or two very quickly. Okay, this was a rather easy section. I would not say that, claim that, it's in 1 hour we looked at what is total stress, effective stress and measure. We looked at the how the soil capillarity comes into picture. We'll do an example of soil capillarity next time. We also looked at how the stress distribution varies top to bottom as the total stress, effective and the pore water pressure changes. Remember, you can only measure the total stress and the pore water pressure. You can derive the effective stress, not measure the effective stress. Any question, please? Last chance, because we have the next instructor waiting, and I would not like them to wait. Okay, it seems the section was easy, or I'm not sure if everyone has gone sleep or everyone has left the room. But thank you very much. We'll meet next time.